Okay, so what I want to look at now is the difference between what's known as a chemical reaction and a nuclear reaction. So both of them are reactions between atoms, and they're resulting in a change from what you start off with. So just if we remember, so if we have a look here, so on the left hand side we have nuclear reactions. So we'll just put an N here for nuclear. And then on the right hand side we have chemical reactions. Now, ultimately, the way to kind of think about it is nuclear reactions. The nuclear reactions involves the nucleus of atoms. So it's a change in the nucleus of the atoms. So if we remember, like if we have a look here, so we have the electrons that go around the nucleus, and then inside the nucleus then you have what are known as, so you have protons, neutrons. So protons and neutrons. So they're the main two subatomic particles that make up the nucleus. And then on the outside then you have what are known as electrons. And in a nutshell, the difference between nuclear and chemical reactions involves a redistribution and a change of the electrons and just how atoms pair up with each other. And what keeps the atoms together are the sharing or the giving up or the movement of these subatomic particles that are known as electrons, which are negatively charged. So that's chemical reactions. Whereas nuclear reactions, on the other hand, they involve the nucleus of the atom, and they involve a change in the nucleus of the atom as well. So what actually happens is you end up, like normally, well, for two of the main types of nuclear reactions where you have alpha decay and beta decay, what actually happens is your atoms change into different atoms. So they actually change. Whereas with chemical reactions, what happens is, two atoms might come together and they form a molecule or a compound, but the atoms themselves remain unchanged. Whereas with nuclear reactions, the atoms actually change into different atoms. So we'll look at like two examples. So here we have, so if we look at this example here, so we have the example of sodium and chlorine. So imagine you have sodium, which is represented by Na, plus chlorine, okay, and they react with each other and they produce sodium chloride, NaCl. So essentially what's happening is this atom is joining to this atom. So this here is just a representation of what's happening. So here we have our sodium and here we have our chlorine. What happens is sodium gives up one of its electrons, so it gives it up to chlorine. Chlorine takes up this extra electron, as we see here. And then what happens is, so because sodium has given up one of its electrons, there's more positive charge now in the atom than negative charge. Remember, protons carry a positive charge, and neutrons don't carry any charge, and electrons carry a negative charge. Now, because there's more positive charge in the sodium that's given up the electron, it becomes a positively charged ion. And then what happens is that electron that sodium gave up, chlorine takes up that electron. And as a result of that, there's an unbalance. So there's more negative charge now in chlorine than there is positive charge. So it becomes negatively charged. So then essentially you have this positively charged particle and this negatively charged particle, and they attract and come together and they form what's known as an ionic bond, and that's chlorine. If we have a look at this reaction down here then, so this is a reaction of, so you have hydrogen, and it comes into contact with oxygen. Now this is in balance, and then essentially what happens is you get H2O. Now in this case what's actually happening is, instead of, again, it just involves these electrons on the outside of the atom, And basically what happens is the hydrogen comes into contact, both hydrogens come into contact with the oxygen, and they share the electrons. They kind of share these electrons with each other. And as a result of that, they connect together and they become a molecule of water. So essentially, if you like, they hold hands, basically. So you have this oxygen atom holding on to this hydrogen, or hold on to both of these hydrogen atoms. And what's happening is they're actually sharing electrons with each other. And essentially what atoms are trying to do is they're trying to become more stable. So they are. And by arranging themselves in these arrangements, they're physically and energetically more stable. So they are. So these are chemical reactions. So you can clearly see the electron, okay, these negatively charged subatomic particles are the key in relation to chemical reactions. So they're the glue that hold these atoms together and cause them to react. Now, if we contrast that with nuclear reactions, which these types of reactions are completely different. So nuclear reactions actually involve a change within the nucleus of the atoms that are involved in the reaction. So if we take, so this substance here is known as americium, and this here is the nucleus of americium. It's not shown the electrons because we're not really concerned with the electrons with nuclear reactions because they're not involved in the reactions, but it's the nucleus. And what, like, something is radioactive when the nucleus of the atom spontaneously just breaks down. So there are some nuclei of certain isotopes of elements that are just unstable, and as a result of that, they want to jettison off, or they want to get rid of some of their particles and some of the energy so that they can become more stable. So when we look here at this reaction here, so you have the reactants on the left and you have the products that are produced on the right. So if we have a look at this, like, how do we first of all write this nuclear reaction? So we can write it like this. So first of all, we have Am, which is the chemical symbol for this compound that's radioactive. We put the atomic number, which is 95. And remember, the atomic number represents the number of protons that are present in the nucleus. So americium has 95 protons in its nucleus. And then we put in its atomic mass, which is 241. And this 241 is a combination, it's the 95 protons and then plus the number of neutrons that are present. So what we can see here is, so imagine these green circles are protons and these blue ones are neutrons. So what starts to happen then is, during a nuclear reaction, and in this case we're talking about alpha decay, this americium nuclei, it starts to break down and it starts to jettison off. So as we can see here, it generates these alpha particles. And if we look at an alpha particle, it's made up of protons and neutrons. So we can see that there's 2 protons and there are 2 neutrons. Okay, so what's going to happen is this number, which represents the number of protons, is going to reduce by 2, and this number, which represents the number of protons and neutrons, is going to reduce by 4. Because we have 1, 2, 3, 4, 4 subatomic particles in the nucleus that are all of a sudden jettisoned off. So what's going to happen is these 2 numbers are going to reduce. So it's going to change into a different substance. So if we put in this symbol here, and what we'll do is we'll put in this new atomic number. So the atomic number is going to, so if we have 95 protons starting off with and we lose 2, we end up with 93. 93 protons, this is the number, the atomic number. And then also as well, this number here, 241, reduces by 4. And that we're going to end up then with 237 as its mass number. Now, that represents this here. Okay, just we're writing it in chemical notation. So we have this new substance formed, and then we also have this alpha particle that's generated off. And if we look at the alpha particle, so He, so it's actually the nucleus of a helium. And what do I mean by that? It has 2 protons and it has atomic mass of 4. And then we have, this also generates a lot of energy as well. So this like what we're looking at here, so this is a nuclear reaction, and what happens is we have a new substance that's formed. And this here then is the official definition of a nuclear reaction that involves alpha decay. So when an isotope undergoes alpha decay, so it's called alpha decay because these things that are jettisoned off by the nucleus are called alpha particles. Its atomic number, which is, so its atomic number, okay, and this is the atomic number, decreases by 2. So we can see here it decreases by 2. So we see it's gone from 95 to 93, while its mass number decreases by 4. So we'll just do this in a different color. So its mass number decreases by 4. So this number here that's at the top represents the mass number, and we can see it's gone from 241 to 237. So it's reduced by 4. And then this is what's generated out. So essentially what you're getting is you're getting one atom that's changing into a different atom, and what's happening then is it's giving off some kind of decay. In this case it's alpha decay, so it's giving off this helium nuclei. And if we remember the atomic number, which is the number of protons, that's what distinguishes one atom from another atom. So if we have a look, at americium, so it's the 95th element on the periodic table. So if we go in here and look at the periodic table, so we can see here, so the periodic table increases by its atomic number. So this number that's at the top represents the number of protons that are present within the element. So we can see here helium has 2. So helium in this case, it has, so this helium has 2 protons and then it has a mass of 4, and that's essentially what a beta particle is. If we have a look then, so we're looking for, so americium is the 95th element. So the 95th element, so we can just look along here and find it. Okay, and there it is there. So this is our 95th element. So this is what we started off with. Okay, maybe not do it like that. Maybe something a bit lighter. So this is what we start off with, americium. And what happens is the atomic number reduces by 2. So if we see here, it's actually going down the periodic table. So we're going from here to here. And this is what's being generated. So this is our new element that's formed. And then what happens is it jettisons off a beta particle, which is essentially just the nucleus of a helium atom. So that's physically what's happening. Whereas if you take sodium, like if we take the chemical reaction, for example, you have sodium essentially sticking on to this chlorine over here, but both atoms, there's like in the product there's still sodium and there's still chlorine atoms that they're just joined together, but with a nuclear reaction they actually change completely. Okay, so that is what's known as alpha decay, which is that's that type of nuclear reaction. Then if we have a look down here, this one, so what we have here, we have, so carbon 14. So again, we have the nucleus of a carbon 14 isotope. So carbon 14 is an isotope of carbon. It's unstable, therefore it's radioactive, so it wants to break down. Now, what happens with the, so we're talking about beta decay in this case. So we'll notice here, so we can see that in blue, these blue circles represent neutrons and the red circles represent protons. So what's actually happening is a neutron, okay, is changing into a proton. So you can see here. So what happens is this neutron changes into a proton. And remember, the number of protons is what distinguishes one atom from another. So essentially what you're getting is you're getting a carbon atom changing into a different atom that has one more, that has an, so the atomic number increases. So what we have here, we can represent this like this. So we have carbon, and I'll just write it over here, so carbon. So the C represents the chemical symbol for carbon. We have this number at the bottom, which is 6, which represents the number of protons that are present, and then 14, which represents the number of protons and neutrons. We indicate an arrow. This indicates that this carbon 14 is changing into something. So what it actually changes into, it changes into nitrogen. So nitrogen, so the symbol for nitrogen is N, and the atomic number for nitrogen is 7. So we see that this neutron has changed into a proton. So we started off with 6 protons, now we get one more, so this bumps up the atomic number to 7. And what happens is the mass number actually stays the same, because protons are equal to neutrons in relation to mass. They both have a mass of 1. So what happens is then you get this neutron changing into a proton. Now what happens then is that there's a difference in energy, and that energy has to be given off. So what happens is it gives off what's known as beta decay, or a beta particle, which essentially is just an electron. So what you get then is you get this high energy electron being jettisoned off. So we can just use the symbol E to represent an electron, -1, which represents the charge, they're negatively charged, and then a 0, because the mass is very, very small, it's almost negligible. Plus, you get a lot of energy. So if we have a look here, so this is the reaction, nuclear reaction for carbon 14. So this then is the definition of it. When an isotope undergoes beta decay, so beta decay, so these are your beta particles, which is essentially this high energy electron. Its atomic number increases by 1. So if we think of its atomic number, so this here is it starts off as 6 and then it increases to 7. So that's what we mean. Its atomic number increases by 1, while its mass number remains unchanged. So if we think about this as its mass number, so you can see that it just remains the same. It stays as 14. So, and this is what's known as beta decay. And again, this is what's known as a nuclear reaction. So again, if we have a look at this on the periodic table, so first of all, if we have a look, so carbon, so this is what we're starting off with. Okay, so carbon, and it's carbon 14, which is the isotope of this. We can see that carbon has 6 protons. Now what happens is one of the neutrons in the nucleus turns into a proton, so that bumps up the atomic number by 1. So it goes from carbon to, it changes from carbon to nitrogen. So you have nitrogen here. And that's essentially what happens. And then what it does is it gives off an electron, so a high energy electron. So again, like this reaction, chemical reaction, so you're essentially getting one atom being changed into another atom. So that's, let's say that's carbon 14, and that's beta decay. So you have alpha decay and beta decay, and it's just comparing the two types of chemical reactions. So some kind of typical questions that you could be asked in relation to in relation to questions around nuclear reactions. So they can be something like this. So what you're being asked to do here is write an equation for the beta decay of the radioactive isotope. So this is what you're starting off with. So you're starting off with oxygen, the oxygen 19. So remember, this 8 represents the number of protons, this 19 represents the mass number. Now if we think about beta decay, what's actually happening? So if we remember with beta decay, its atomic number is going to increase by 1. So that means that, so when this reacts, so this number at the bottom is going to change to 9, and the number at the top, 19, is going to stay the same. So what's it actually changing into? So oxygen is changing into an atom that has 9 protons. So then we just go back to our periodic table and we have a look. So if we look, here's oxygen, it has 8 protons. Here's an atom that has 9 protons and it's fluorine. Okay, so its chemical symbol is F. So we put in that chemical symbol here to represent that the oxygen has now changed into fluorine. And then what happens is you get this high energy electron that's being emitted. So you have E, this just represents that it's an electron and it has 0 mass. So this here is your, so when the oxygen 19 isotope undergoes beta decay, its atomic number increases by 1 while its mass number remains the same. So then this here will be your answer to that question. If we have a look at this one, write an equation for the alpha decay. So the alpha decay of the radioactive isotope. So this here is lead. So we'll just write this down. So Pb, and you have 82 protons, and you have 202. Its mass number is 202. Now if we think about what's happening with alpha decay, like if we go back up here and have a look at alpha decay, so essentially with alpha decay, its atomic number decreases by 2 while its mass number decreases by 4. So what's going to happen is this number here is going to decrease by 2, so that's going to change to 80. And then this number up here, which is the mass number, that's going to decrease by 4. So that's going to become 198. So 198. So then we have to think about what atom on the periodic table has 80 protons. So again, we go to our periodic table. So we look for 82, which is what we're starting off with. 82, there's lead there. And what's happening is it's dropping down to this guy here, which has an atomic number of 80. So that's mercury. So you get lead being changed into mercury. So its chemical symbol is Hg. So we just put in the chemical symbol. So it's Hg. So that's the chemical symbol for lead. Then you have to represent the alpha particle that was generated. So remember, an alpha particle essentially is it's just a helium nuclei. So it just has, there's 2 protons and 2 neutrons attached together. So you have this 2 represents the number of protons, 4 is the mass number, which is made up of the 2 protons and the 2 neutrons. So that's why it's 4. And then so this essentially then is the alpha decay. And if we remember, so just if we have a look here, so this is alpha decay. So this here is your alpha particle. So it's essentially just 2 protons attached to 2 neutrons. And if we think about 2 protons, like what atom has 2 protons? It is, if we look on the periodic table, so helium, we can see it's 2 protons. Now, the difference in this, in the helium atom and this helium alpha particle, is that this isn't going to have any electrons around it. It's just going to be a nucleus. And that is like so these are the types of questions then that you could be asked, you know, to work out in relation to nuclear reactions. So that's it. Hopefully that makes sense. So what we've looked at then are Chemical reactions versus nuclear reactions. Chemical reactions involve the changing around and the sharing of electrons between atoms, and they join up or break apart. But the atoms themselves remain the same. So when sodium and chlorine react together, there's still sodium and chlorine in the finished product. The same with hydrogen and oxygen. When they react together, you still have hydrogen and oxygen, but they're now connected together in a molecule of water in this case. Whereas chemical reactions, or nuclear reactions should I say, what happens is the nucleus, the atoms change from one atom into another, so that they physically change, and it involves the nucleus of the atoms. So hopefully that makes sense, and that kind of gives you a little bit of understanding of chemical reactions versus nuclear reactions. Okay, thank you for listening.